Hello, chemistry students. So again, we continue with equilibrium. This time we're going to introduce a few concepts, most of which are just review, but we're going to look now at acid-base equilibrium to prepare us for what is coming up next. Okay, so let's review, and I'll explain why I have all of these. Usually I tell more of a story when I'm in class, but when we're in class, but might have to skip some parts or just tell you the short version of it. Okay, so to review grade 11, we look at then the Arrhenius theory of acids and bases, and here we see that according to this definition, an acid dissociates to produce hydrogen ions, or we now know that it can actually be hydronium ions. A base associates to produce hydroxide ions, and that definition is not incorrect. It's very, very correct. It's very true. Okay, but there's just more to that you learned in grade 11. So there were some certain substances did challenge this definition. Ammonia is certainly one of them. They tend to act like bases. Well, these two, sodium bicarbonate, both of which tend to behave like bases, and yet you can't see that any of them have hydroxide ions. Right, so this old definition, just like this old laptop, I usually tell a story about going over to a friend's house to work on a science project, actually, and seeing one of these things, his dad's laptop. This was a mammoth briefcase, larger than a briefcase size. Anyways, that's that. And why this person's here, I might give away my age, although don't usually try to hide it, but I like watching Star Trek, and there's a reason why I have Lieutenant Commander Worf here because of the next definition. Okay, so to explain why these substances and others behave like bases despite them not having hydroxide, we amend the theory, add to it actually, the Arrhenius definition of acids and bases, now known as the Bronsted-Lowry definition. Okay. So after these two scientists, this Bronsted-Lowry definition essentially says this. Bronsted-Lowry acids, and I will get back to Worf in just a second. A Bronsted-Lowry acid is defined as a proton donor. Okay, so it's going to give away a proton, which is really just that. Okay, so an acid is anything that can give away hydrogen ions, and a base then is something that will accept it. So this gives away, and bases will then gladly accept. Okay, so in this example, we have an acid, acetic acid in this case. Acetic acid, you see, look at the conjugate or the pair that match. We have acetic acid here and this conjugate here. They are both not the same, but one comes from the other. And we see that the difference then is that this hydrogen ion has been donated, right? Donated. That makes this an acid. Okay, now sticking to the left side, to the reactant side, water, let's compare water to its conjugate. Its conjugate is right over here. Okay, what happens to water? H2O then becomes H3O+. So what's happened to it is that it has accepted a proton. So if it's accepted a proton, that would make it a base. And so it is an acid here and a base for water. Now the conjugates are always the opposite. So this base, water behaving like a base, will then produce a conjugate acid. Look, this is likely to give up, if allowed to, that hydrogen ion here, and we know that the hydrogen ion and hydronium are acids, of course, so it makes sense that this is a conjugate acid, which came from the base. And this is a conjugate base, right? Your acetate ion here that came from acetic acid. Okay, so this can behave like a base. It could move in the opposite direction, as these arrows indicate, to accept then a proton, therefore behaving like a base. So wrapped up grade 11 acid-base definitions all here. Now why Worf is there, I remember when I was in, I think this was grade 11, bad PLAR, I don't know why I still know this, but it's stuck. And it's just a mnemonic device that says Bronson acids donate protons, Lewis acids receive electrons. Okay, you don't have to know the Lewis definition of acids and bases in this course. You can look it up. There's more to this definition. So ended up getting rid of this, and what we end up with is, so why Worf? Why the Klingon from Star Trek, the Next Generation series, awesome series? Why Worf? Because it just kind of sounds, bad PLAR sounds like Klingon. That's why. Okay, but the mnemonic device that you can that I can share with you that makes more sense, I guess, is bad proton. Bronsted acids donate protons. There you go, an easy way to remember that, although this really isn't too hard to remember. Okay, so that's just a review of acid-base definitions from grade 11. Now, you having grade 11, you did, I'm sure, talk about the nature of water and how it is amphoteric. Water can behave as both a base and an acid. Look at our example here. We've already seen how water can behave like a base. It can accept a proton to become a conjugate acid. Water can also, and look, here's ammonia. Water can also donate a proton, which makes it behave like an acid. And therefore, the conjugate version of that would be a conjugate base. Look, here's your hydroxide, of course, behaving like a base does. And this shows you why ammonia in the presence of water can actually yield ammonium and hydroxide, thereby behaving like a base, yet not actually having a hydroxide in its structure. Okay, so water is amphoteric and behave like an acid and a base, to summarize. Okay, so even pure distilled water can conduct electricity. Now, what does this have to do with water, with ions? It's not a great conductor, actually. Distilled water. I mean, if you measure the conductivity of tap water, you'll certainly see that it can conduct electricity quite well, because there are a lot of ions dissolved inside tap water. But if you take distilled water, you'll see that water can conduct electricity, and that gives us a hint. It means that there must be some ions present in there to allow for that conduction of electrons, for allow electrons to pass. So to add to the nature of water and its amphoteric properties, we see that water can actually self-ionize. Okay, so this self-ionizing doesn't happen. It's low. It does happen, but its concentrations are so low, it doesn't happen to a significant amount. Okay, bit of review here. In a perfectly neutral solution, we have concentration of hydrogen and hydroxide equal to the same. In an acidic one, well, you get the idea. More acid, more hydrogen ions. In a base, therefore, more hydroxide ions, right? So since water can auto-ionize all by itself, leave distilled water in a clean beaker container, you will see that water does. I'm going to write HOH, but water can self-ionize, right, to produce hydrogen and hydroxide ions. Now, this will give us the ability then to write a Kw expression. Look, you would ignore water because it's liquid, but you would consider the concentration of hydrogen and hydroxide ions. And when you do that, what you end up with is a value for Kw that is very low, right? But it is still important and will help you solve problems in the very near future. So empirical data shows after much experimentation, throughout the world, it's been agreed upon that the Kw value, which is represented then by this expression, right? The auto-ionization of water, represented in an equilibrium expression as Kw, has a constant value of 1 times 10 to the negative 14, again, at a given temperature. Okay, so this value is important, one of constant value that you will need to know. Okay, back to grade 11. Just throwing this all out here because it's all review. I'm tempted to just skip over to the next slide, but I'll briefly talk about this. So to find pH, it's dependent on the concentration of hydrogen ions, not acid. So if you have HCl or H2SO4, it's not the concentration of these guys that are used to figure out pH and plug directly into here. It's not. Instead, it's the concentration of your hydrogen ions from the dissociation or ionization of these acids. Okay. Now you can play around with this math a bit, and you can then figure out, do the opposite using pH. You can find the concentration of hydrogen or hydronium ions. POH is done in a similar way. Now, the way that pH and POH are related is that if you take the value of pH and POH, add them together, you get 14. That means with one, you can find the other. So with POH, you can find pH. And with pH, you can find POH. Okay, so just in a nutshell summary of what you did in grade 11. So this is how they're all, again, related. Right, your pH and POH scales are here. Now you've usually seen your pH scale range from 1 or 0 all the way to 14. Now it can go beyond these values in either direction. What is strange often is that we aren't usually exposed to a pOH scale. So just to point out here, an acidic pH value, let's say 2, quite low on the pH scale, on that common pH scale you've often seen. A pH of 2 would mean a pOH of 12. So it's just the opposite. A high pOH tells us that it is actually an acidic solution. Low pH tells us acidic as well, right? So it's just the opposite between pH and pOH. And that's it. A bit of a reprieve from our longer lessons. Here's your home fun, straight from your textbook. If you have any questions, let me know. Hopefully this helps.